Hi there guys, well welcome back. We've just done 4U, which was all about implicit differentiation, and we're now about to tackle the last exercise in this unit, 4V. Okay, and 4V is all about related rates of change. So in the previous exercise with implicit differentiation, we were always looking to find dy dx and then do a rearrangement perhaps in order to factorize out dy dx and get some expression in terms of x and y. Now, in this exercise, we're talking about questions in context, and often there will be other related rates of change involved in the question, which might just be left there in your answer. So, for example, in this question here, they're talking about dv dt, so how's the volume changing with respect to time, dr dt, so r here is a radius, so how is the radius changing with respect to time, and likewise how is h changing with respect to time as well, dh dt. And so when we do our implicit differentiation, we may end up with other related rates of change which aren't dy dx. Okay, and we'll see that through this question. So I've just copied this one across onto here, and this one says a cone-shaped paper cup is being filled with water. So we've got something like this, and it says the volume of the cone is given by this, so we know this from before. We're not being asked to prove it, we're just being given this thing. So a third of the volume of a cylinder is the volume of a cone. And we've obviously got our height in this case and our radius of the circle that we're getting at the top there as well, here and here. Okay, so it says use implicit differentiation to find an expression which links dv dt to the rate of change of the water's volume. So for example, that might be the tap that's filling this thing up might be flowing at a particular rate, and that will also be equivalent to the amount at which the volume is filling up. Okay, so that's the rate of change of the volume's water, and then dr dt, the rate of change of the water's radius. So as this circle gets higher, as the height of this water gets higher, then the radius of the circle is going to get bigger. So we're interested in what's the rate of change of the water's radius, and also what's the rate of change of the height. And you can imagine if the water is just sort of flowing through here at a constant rate, so if dv dt is constant, then the height is going to fill up much quicker at the start than it is towards the end, because there's a small amount of volume needed for this, but that last section of height is going to be a large amount of volume which needs to fill it up. So some of these might be given to you as constant. You might say volume is increasing at a constant rate. Okay, so then it says interpret your answers in the context, answer in the context of the problem. So we're looking at this and thinking, well, how do we create dr dt and dh dt? Well, maybe I'm not sure to start off with, but I know that I can just ddt this thing here, and I know everything else is in terms of dt as well. So what I'm going to do is use d dt as an operator on v. Okay, and I can see that this is not defined in terms of t. So r, though, will depend on t because the radius changes over time, and h also depends on t because that also changes over time as well. So r and h are both functions of t. So we can take out our constants. We're getting a third pi. We can just take that outside the front. And now we're having to apply d dt of this section of the right-hand side here, the r squared and the h, so the product of r squared and h. Okay, now we know that r is equal to r, is some function really of t, and so is r h in this case as well. So we're now going to use the product rule on this. So we can say u is equal to r squared. In r, by the way, not a b. Okay, and that's an h, not a b. Okay, So, and u is equal to r squared and v is equal to h. And now we can say our d dt of r squared h is going to be equal to u, which is r squared, times by the derivative of v. And the derivative of v is just dh dt, okay, because we're saying let's differentiate this with respect to t. Well, because v is h, we can just say dh dt. No chain rule needed there. And so now we've got u and v dash, and now we need v and u dash. So v is just plus h, and we need to differentiate this thing here. So we need to differentiate u with respect to t. Well, differentiating u with respect to t, well, it's in terms of r squared. So with respect to t, so let's just take that back and say r squared with respect to t here. So this. So what are we going to do? We're going to say d of r squared with respect to r, which we know how to do, and then we're going to be left with dr dt in order to get this dt at the bottom. Okay, so in order to differentiate this r squared with respect to t, we're going to apply the chain rule essentially. Okay, so we can't differentiate this with respect to t. We can differentiate it with respect to r, then we need to chuck on this extra dr dt at the end. Okay, so we're going to end up getting 2r and then dr dt. So we're going to get here 2r, which is the derivative of this, but you need to remember to chuck on the end here your dr dt. Now you can put all of this back in for this thing up here. So we're now getting a third pi of everything which is there. So all of this. And so we can say we're getting a third pi, and let's leave it factorized. In fact, we're going to get r squared dh dt and dt, and then we're getting plus 2rh dr dt. Okay, so we're pretty much done. That's the final answer to VDT, and we've now done what they've asked, I think. Let's just see again. They've said use implicit differentiation to find an expression which links dVdt to drdt and dhdt. So essentially all we had to do was differentiate with respect to t. And we've done that, and we've had to use implicit differentiation here, and within that we use the product rule and we use the chain rule as well. Okay, so now we've got this, and the final bit says interpret your answer in the context of the problem. Okay, well, it's basically saying that the VDT, the change in the volume over time, so how quickly the volume is changing, is dependent on a couple of things. It's dependent on how fast the height of the water is changing, or how the height of the water is changing, and also how the radius is changing as well. So now if we assume that the dVdt is positive, then given that the cone is fixed, the cone's measurements aren't going to change here, then if we're going to have an increasing volume of water, well, that will depend on dh, the height increasing, and also the radius increasing as well. And there is a rate of change of the radius, and there is a rate of change of the height. Okay, well, what does it say in the book? Let's just read this one out as well, because I'm not sure my explanation was great there. So it says the rate at which the volume of the cone changes is related to the rate at which the radius and the height change. Okay, so remember that whenever we're talking about dt, something dt, ddt, we're talking about the rate of change of that variable. Okay, so dv dt is the rate of change of the volume. The hdt is the rate of change of the height. Okay, now this also says as the volume increases, the height of the water level and the length of the radius of the water level also increase. Okay, I guess that's true. I'm not sure you can say that from the formula dv dt. I mean, potentially dr dt increase, dh dt increase, and r and h don't increase. I struggle to see that from the formula there. I think we're good enough in an exam situation to say that dv dt depends on dr dt and it depends on dh dt as well. And sure, yeah, it also depends on R and H. Those two things are in the formula as well. And clearly, if the volume is increasing, the only thing that can happen, given the the sort of physical situation, is the radius and the height can increase. So I suppose it's true to say that dV/dt does depend on the radius, the height, the rate of change of the radius, and the rate of change of the height as well. It depends on those things. Okay, and because of the physical nature of the problem, it's when the radius or the height increases, then dV/dt increases as well. Okay, I'll stop there. I'm kind of tying myself in knots a little bit there. You can see what their explanation is. Okay, right. So there's other related rates problems here. They to talk about other situations, and you'll see these in the questions. They say, for example, there's other real life situations like the rate at which air is pumped into a balloon affects the rate at which the balloon's surface area changes. So the surface area change is related to the rate of change of the volume. Okay. The rate of change at which the water is released from a reservoir affects the rate at which the water level in the reservoir changes. That's a bit similar to the last question. And the third one that says the speed of a car affects the rate at which the car consumes fuel. So again, we're talking about rates there. Speed of the car is, ddt of the distance. So, or dsdt, if you like, if we're talking about velocity, affects the rate of the car consuming fuel. So that would be df dt. Let's just look at that first one. Let's take that one as an example. Okay, so the rate at which the air is pumped into a balloon affects the rate at which the balloon's surface area changes. Well, let's consider that a balloon might be spherical, and the volume of a sphere is V is equal to 4/3 pi r cubed. So there's our formula for the volume per cubed. Now, if we wanted to say here dv dt, and again, we've only got one variable here. We've got the r. This is just a constant. We can take that constant out the front, and then we're going to need to differentiate this. So we can say here we've got dr cubed dr, and then we've got our d r dt there. So we can put that in. Now actually I'm going to put that in a slightly different form here, because actually what we could do is this. We could say that that's the same as dv dr times by r dt. Okay, now the reason why I've done that is because you can see again we've got the chain rule by just writing out our different derivatives there. And sometimes you can just do this whole thing by writing out derivatives as these kind of seeing them as kind of fractions. Okay, so that's the same as saying the VDR, well, let's take out the 4/3 pi, and then we're being left inside with r cubed, and then we're doing the r dt. So you can have these kind of strings of derivatives sometimes in your questions here. So although we're dealing with this with implicit differentiation, I think that's what I was saying at the start of the last exercise, saying, well, implicit differentiation is the sort of overall technique which we're using here, but sometimes it can be split up into just one single use of the chain rule, or maybe two uses of the chain rule. Okay, so here we go. If we differentiate this, we're getting 3r squared, getting 4/3 pi. The 3 is cancelling out there, and we've got the dr dt on the end. Now that's kind of interesting, because actually we've got there 4 pi r squared is the surface area of a sphere. It's the formula for the surface area of a sphere. So yeah, sure. We've got here the rate of change of the radius So the rate of change of the rate of change of the volume is dependent on the rate of change of the radius times by the surface area here. I think that's just a bit of a coincidence, really. But they're saying that volume and surface area rates of change could be related as well. We really need to look at the question to look at that. A little bit of what I was saying before, though, as well, is just some of these can occasionally look like big strings of related rates of change or big strings of the chain rule. So, for example, if I said A is equal to a function of g of x, then if I wanted to do dA dt, well, that would be the same as doing dF dg. Remember, f is in terms of g, and then dg dx. Remember, g is in terms of x, and then dx dt there as well. So you might end up with these kind of whole strings of the chain rule, essentially. Okay, that's one little point. Another little point, which the book doesn't mention but might be useful at some point for you, is that if you want to know what dV dt is, and you've got, in fact, dt dv somewhere or other, because you've used strings of chain rule, then you're allowed to use the fact that the 1 divided by the function dt dv is going to give you dv dt. In other words, dv dt is equal to the reciprocal of dt dv. Okay, you can use that one. So that's not proved there, but if you get stuck in an exam situation and you find that you've got your derivative the wrong way round, you can actually just take the reciprocal of it. That is allowed. Okay, there's a little deviation there, but let's look at example 39. There's some sort of hints there. I think I've talked enough now. Let's go on to example 39 and deal with this one. So it looks like it's using Pythagoras there. So this one says a 25-meter long industrial ladder is leaning against a wall on a building site. So we're getting something like this thing here. The bottom of the ladder starts to slip along the floor at a rate of 0.2 meters per second. Okay, so we've got some sort of height and we've got some distance across. Now determine how fast the top of the ladder is moving down the wall. Okay, so this is moving down. Okay, so we're interested in what's the change in this. That's what it's asking us to do. Determine how fast the top of the ladder is moving down. So we want to know what's the dy dt at this top point here. And yeah, we don't know where that is on there just at the moment. But we definitely know that dx dt at this particular x point here is going to equal to 0.2 meters per second. So it's moving at 0.2 meters per second. That's dx dt. We also know that the ladder is 25 meters long, so we know that we've got x squared plus y squared is equal to 25 squared there. Okay, so that's just Pythagoras, because we know we've got our height of y and our distance across of x, and we've got a length of 25 there. Okay, and it says determine how fast. That's what we're looking for. We're looking for this. The ladder is moving down the wall at the instant when it is 20 meters above the floor. Okay, so we're getting some more information here. We want to know this when we've got y is equal to 20. Well, what's x at that point as well? I'm just kind of interested to know. Might be useful for later. We've got x squared equals 20, sorry, plus 20 squared, which is 400, is equal to 625. We're getting x squared is equal to 225. The square root of that, and it can only be positive, by the way, it's going to give us 15. Okay, so we've got the coordinate point there. We've got 15 on this axis, and we've got 20 on this axis here. Okay, interpret your answer as well. Okay, so I'm looking at this and I'm thinking there's definitely dt involved. There's definitely dy dt and dx dt involved. And the only way I can see of doing this is now to differentiate this whole thing implicitly by thinking, okay, well, let's create those dt's by doing ddt of every single thing that you've got here. So we're going to do ddt of x squared and ddt of y squared, and we're going to do ddt of this constant at the end, 625. Now, to be honest, when I'm looking at this, I don't really know where this is going. But I know that I need to create these dt's on the bottom. I know the only way of doing that is to do some differentiation with respect to t. And I haven't got a formula for like a geometrical situation for the volume or the surface area or anything. So I'm just going to differentiate the whole thing implicitly. So let's do it then. So when I differentiate this, I'm going to get 2x, and hopefully you're getting the idea now. Just saying, well, we're going to put on dx dt on the end. Differentiate this in the same way. I'm going to get 2y I dt, and then the derivative of a constant is 0. Okay, now we don't really need to rearrange this. Although we're looking for dy dt, you could do your rearrangement of this and say, okay, well, let's take this from this side and let's divide by 2y. But frankly, you don't really need to do that because now we've got enough information to substitute into this equation. So we've got our 20 and 15, which we can put in here and here. We've also got 0.2, which we can put in there. So it's just a matter of solving an equation now, and I just substitute those things in. So 2 lots of 15 is going to give us 30. The x dt is 0.2, so we need a fifth of 30, which is 6. And then we've got 2y, so 40 there. And then we've got this dy dt. Okay, so the 6 we can take over to the other side. Let's just scratch that. The 6 we can take over to the other side. So we're going to get minus 6 divided by 40 is equal to your dy dt. Okay, and you know, whatever that gives you as your answer, to be honest. Okay, you can write it as a fraction, or I would personally just actually work out what it is and then write that as your answer in terms of meters. Now, I think that's pretty beautiful as an answer there. We've interpreted this geometric situation which is going on here. We've now changed it into just an XY problem to talking about a related rates of change problem. You know, if this is moving at a certain speed, at what speed is this moving at? And I think that's really, really quite nice as a way to finish this chapter. These are really nice questions, but they are quite difficult to sort of set up in the first place. Okay, so there we go. Let's just see. Yeah, it's giving us minus 1.5 meters per second there. You can see that they haven't rearranged to make dy dt there either. Okay, so there's that done. You've now got 10 questions to practice on there. And then finally, it's talking about, now it says, now do the modeling and investigation activity on page 302. It's telling you to go backwards. And where's 302? 302 is telling us to go forwards. It's saying that you could do this river crossing thing. Okay, so that's quite nice. There's a river crossing problem there. It's obviously going to be relatively tricky, and this is a problem which you could potentially do as an IA and then make it more complicated. So that would be a nice starting point for an IA. Okay, there we go. And you can see obviously there's your usual, gosh, there's a lot here on the chapter summary. So there's a ton of stuff in the chapter summary. If you want to make some notes on these things, just to review things. And then we've got your chapter review. I mean, really good questions to do here. A ton of questions, 23 questions there before you get to the exam style questions. But you can see the mixture of questions, they're all exam style anyway. And then, of course, you've got your exam style questions. That's taking you up to question 33 as well. So it's an absolute ton of practice in this excellent Oxford book. Okay, guys, well, thanks for listening in. Well done for your efforts during this chapter, and I hope to see you back for the next one.